previous class at this point where we were discussing about the infiltration process, right? So we discussed these different zones that are present when there is infiltration going on, and what the significance of these zones are, and what their characteristics are, and so on, right? And then after this, we moved on to discussing infiltration capacity, which is of interest for us because it determines how much water will be infiltrated by a particular soil for a given rainfall event, right? So it is the maximum rate at which a given soil can absorb water. Now, I don't know if you have read the news. Has been receiving a tremendous amount of rainfall in the last 1 or 2 days. So that's I think they received 300 millimeters of water in the last 24 hours or something like that. So massive rainfall amount. So that is the kind of situation where it becomes important for us to know how much water can the soil in a particular region absorb, because how much it can absorb tells us how much will be left over as runoff, which is what is causing the flooding and all of the issues that are taking place in across the country, right? So the infiltration capacity is a very important parameter of interest, right? We designate that with the symbol FP. Typically, we denote it in centimeters per hour, and the actual rate of infiltration is not the same as the maximum rate, the infill capacity. Now, the actual rate of infiltration will be equal to the infiltration capacity if the rainfall intensity is greater than the infiltration capacity. But if the rainfall rate is lower than the infiltration capacity, then infiltration only happen at best at whatever is the rainfall intensity at a particular instant of time, right? So that's a fairly obvious implication. Now, then the next question that I asked was, is this infiltration rate actually a function of time, or is it independent of time? And we came to the conclusion, based on a brief discussion in last class, that this infiltration rate indeed is a function of time, because as the soil becomes more and more saturated, right, its capacity to infiltrate more and more water reduces as a function of time. So to begin with, when the soil is very dry, the soil has its maximum infiltration capacity, and then as time moves on and the soil becomes more and more wet, its infiltration capacity reduces over a period of time. So that is the physical understanding that we need to have about the process of infiltration in terms of how it is not a constant value, but actually a function of time. And this is fairly obvious. I mean, you must have seen this, right? You have rainfall happening throughout the day, but initially the flooding doesn't start, because until some time the soil keeps soaking up the water. It's only when the soil's capacity has gone below the rainfall intensity that you start seeing flooding starting to take place, and so on and so forth. Anyway, we'll discuss these aspects as we move on. So now let's look at the instantaneous infiltration rate that we would be interested in knowing at any given point of time, right? So now this instantaneous infiltration rate, we will denote it as f of t, small f of t. It depends on so many factors. It depends on the vegetative cover, it depends on the soil properties, it depends on the current moisture content, so on and so forth, right? Now, along with this infiltration rate, which is of course a function of time, another thing that we are interested in knowing is how much cumulative infiltration has taken place over a given period of time, right? So I have received 2 centimeters of rainfall. How much has become infiltration? Has 0.5 centimeters become infiltration? Has 1.2 become infiltration? Or has the entire amount, 2 centimeters, become infiltration? So now that becomes something very interesting, because, as I said, remember, the chief objective of most of these studies, most of the hydrological, is to find the runoff. And the way to find the runoff is to subtract the infiltration from the rainfall, right? So if I receive X centimeters of rainfall, and if some portion of X becomes infiltration, then whatever is left over is going to be a good approximation for the runoff that's taking place, right? So runoff is the predominant parameter of interest, and therefore we keep all of this is being done in a way to try to find runoff, right? So that's kind of the although we're talking about infiltration, in reality we are more interested in the runoff. Of course, infiltration is also important, but I'm just trying to explain to you how the historical nature of this whole analysis of the development of this of the science focused on runoff as the parameter of interest, because it was a direct computation of the amount of water that will be available for us. Keep in mind that maybe 50, 60, 70, 80 years ago, groundwater was not used very much, right? You could only dig some very shallow wells and take water out of those, right? So groundwater use was not very, very predominant, although it was available everywhere. The predominant source of water was always surface water. So that's why, if you remember, in the beginning of India's independence and all of that, we went on a mission of building dams across the country, right? Because we wanted to tap into the water so that we could use that for irrigation and so on and so forth, right? So and of course we generate electricity. There's multiple benefits. These dams are usually called purpose reservoirs. They provide water for irrigation, for industry, for domestic purposes. They'll produce electricity. They will control floods. There are multiple purposes. Anyway, let's not get sidetracked. So the infiltration, the cumulative infiltration, is basically the sum of all the infiltration that has happened over a given period of time, and it is typically units of length, centimeters or inches, right? And we denote it by capital letter F. The infiltration rate is denoted by the small letter f, and the cumulative infiltration is denoted by capital letter F, right? So it is the accumulated depth of infiltrated water during a given time period. Okay. Now, if you want to think about it mathematically, capital F of t can simply be thought of as the integral of this instantaneous infiltration rate, right? I've used some dummy variable tau to indicate time. So f of tau d tau, you integrate it from 0 to t, whatever is the time period of interest. You integrate it, you get the total sum of infiltrated water that has happened over a given time period. And as you can see, small f has got units of centimeters per hour, length per time, multiplied by time, it gives you length. So therefore, this capital F is simply an integral of all the infiltration rates over a given time period. Of course, the small f is a function of time. It is not a constant value. Of course, there might be some cases where it is a constant value, but in general, it can vary with time. And then, of course, if you are able to get capital F from small f, then you can do the reverse also. If you know capital F, then you can find small f by taking the differential, right? So f of t, small f of t, is d by dt of capital F of t, right? So that will also be something that can be inferred there indirectly. Okay. So now, this is to give you a background of iteration up to this point. Okay, before we move on, any questions? Any questions? I'm assuming everybody is able to hear me clearly. I do have my fan in this room is very loud. I hope it's not causing any disturbance. Anybody can quickly just unmute and say everything's okay, sound wise. Yeah, I didn't hear what you said. Unmute, wait a second, and then speak. Quickly.
Sir, everything's okay.
Excellent, thank you. All right, so any questions? No questions. Okay, so we will move on to talk about specific functions or specific mathematical formulations that are used to describe this infiltration rate, which is a function of time, right? So are these two equations called Horton's equation and Phillips equation. Horton's probably is even more popular. it has a you can say it 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 the form of the equation is of an exponential decay, right? Initially the infiltration rate is high, and then as time goes on it exponentially decays and reaches some kind of an equilibrium value, and it just keeps asymptotically approaches that, right? So that's what it looks like. F of t is equal to f of c, sorry, fc plus f minus fc, whole thing multiplied by e to the power minus kt. So this k is kind of telling us what is the exponential decay, and t of course is time. It decays with time. So if you were to represent this in the of a curve as a function of time, there are two curves here. The first you need to pay attention to is the one that starts at small f naught and then slowly comes down and asymptotically reaches this f naught fc. So this equation very clearly indicates what how the form of infiltration that it takes, physically speaking, right? Although we have automatically, what this means is initially when the soil is dry, the infiltration rate is very high, instantaneous infiltration rate is high. As the time goes on, the infiltration rate of the soil keeps going down and then asymptotically reaches some constant value. Now, physically speaking, you will have to think about this from the point of view of the two processes that cause infiltration in the first place. What are those two? What are those two processes that cause infiltration? The first one is gravity. Second one, the ability of the soil to, gravity does its job in the downward direction. This other force which can cause infiltration is independent of direction because it's a molecular force. It is the suction head, the suction due to the uh, the intramolecular forces of attraction between the soil particles and the water molecules, right? So initially when the soil is dry, the intramolecular forces of attraction, the suction basically is very high. This gravity will always play a role. Gravity is like the constant, right? So you have suction head and then you have gravity head. Both of these together combined gives you this overall phenomenon of infiltration, right? So at initial time t, soil is dry, there's a lot of suction, gravity is also going on. As time goes on, the soil becomes more and more saturated, and eventually a time comes when the soil is completely saturated, so there's no suction left, but gravity is still doing its job. So this asymptotic value that it reaches, f naught minus fc, that is an indication of the the gravity, right, of the infiltration. I mean, the role played by gravity in the infiltration process, right? Initially, it is both gravity and suction, but as time goes on, suction keeps reducing until it goes to zero, asymptotically, of course, and then all that is left is the gravity portion of the infiltration. Okay, so that's what this equation is telling us. Of course, that is the interpretation that we are giving to this mathematical form. But that is how the formulation was also developed, keeping that in mind. Second curve that you see on this is the capital F, which is the cumulative infiltration, right? So the cumulative infiltration initially is zero because at time t equal to zero, there's no rainfall. Rainfall starts and then cumulative infiltration starts to increase. It keeps going up and then it slowly starts to taper off, and then it will reach some kind of a constant rate, and then it will just keep going, right? So that's the second curve, capital F, which is the cumulative infiltration, right? Now this equation does not explicitly characterize the processes by which filtration is happening. It is left to us to understand that this fc and this f naught minus fc, what they are, right? F naught is basically initial infiltration capacity, which is a combination of both suction and gravity, and Fc is the final infiltration capacity, which is only the role played by gravity. Suction has ceased to be a force anymore, right? Because all the voids are completely filled, the soil is getting more and more saturated, and therefore suction is no longer able to play any significant role in causing infiltration to take place, right? So this equation is telling us that, but without parameterizing those terms. Now the second equation that I'm going to show, Phillips equation, explicitly tries to simulate these two components um, uh, 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 of the infiltration process. This is the formulation of Phillips equation. So Phillips equation gives capital Fe as capital S times T to the power half square root of T plus K times T. Right? K is of course the hydraulic conductivity. We've already discussed that in the previous lecture. This new parameter that we have introduced, S, is called the sorptivity. It is a function of the soil suction head, right? So then what this equation is telling us very clearly is that cumulative infiltration is caused by suction plus gravity. K is supposed to refer to the gravity, right? So the first term, capital S, is for suction. The second term, KT, is to indicate that the component of infiltration coming from just gravity alone, right? Which is the property of the soil. Okay, I mean the hydraulic conductivity, which causes the infiltration to happen. And then of course differentiate this equation once to get small f. So you get half S T to the power minus half plus K, right? So that is the form of Phillips equation. And the interesting aspect of this equation is that it is trying to come up with an equation with the physical processes in mind. We have a mental picture of the two processes that are causing infiltration to happen, and therefore we come up with an equation which explicitly accounts for, this is the component that comes from infiltration, from suction, and this is the component that comes from gravity. And so it's an explicit way of writing out these terms that are going into the infiltration process. Okay, now as t tends to infinity, as you can see from here, f of t will tend to k. There's a t to the power minus half in the equation. So as t becomes very large, 1 by under root t will become insignificant, very small. So therefore, this the instantaneous infiltration rate will tend towards the hydraulic conductivity of the soil, which again is kind of mimicking the behavior that you have seen the Horton's equation, the curve over here, right? So as time goes on, this as time tends to a large time, f of t tends to k. So this Fc can also be thought of like the hydraulic conductivity soil, which is an inherent property of the soil itself, right? So it's not it doesn't matter what the condition of the soil is. K value will always be for a saturated soil sample, the K value is just a fixed number. Okay. Anyway, okay. So let's move on. Then, of course, as the two terms represent the effect of soil suction and gravity. And then, if I were to imagine a horizontal soil column, if I instead of having a vertical soil column where the effect of gravity is explicitly visible, if I keep a horizontal soil column, suction remains the only force, because then there is no gravity playing any role in causing the infiltration to happen. So therefore, suction is the only force that plays a role if the soil column is just turned 90 degrees from vertical to horizontal, right? So actually, we'll be solving a problem along those lines, and then we'll see how far we get with that. Okay, let's just go ahead. Okay, before we get to the problem, any questions on these two, Horton's equation and Phillips equation? They are both representing the same kind of physical phenomenon. It's just that they are doing it in different ways. Okay. So anyway, all right. Let's keep going. Yeah. So if I have a horizontal soil column, then capital F of t is s t to the power half, because gravity is not playing any role at all. Okay. All right. Let's just solve this problem and then we'll go ahead. A small tube with a cross-sectional area of 40 centimeters square is filled with soil and laid horizontally. Okay. The open end of the tube is saturated, and after 15 minutes, 100 centimeter cube of water have infiltrated into the tube. If the saturated hydraulic conductivity of the soil is 0.4 centimeters per hour, determine how much infiltration would have taken place in 30 minutes if the soil column had initially been placed upright with its upper surface saturated. Okay, so it's an interesting problem statement. It's an interesting way of formulating the problem. So what the problem is trying to do is to give two situations. One in which I keep the soil column horizontal and then something happens, and using that information you are supposed to infer some parameter which can then be used to solve the second part of the problem, which where I say no, now the soil is no longer horizontal, it's kept vertical, and then what will happen, how much infiltration would have happened, would take place, and so on and so forth. Okay, so then let us go back to the previous slide. Let's just look at this Phillips equation. That's the one that allows us to solve this particular problem. It says if this horizontal soil, if the column is horizontal, then soil suction is the only force. So capital F of t is s t power half. S is the sorptivity of the soil. Okay, look at this problem statement. There is no mention of um, the sorptivity, right? So then what do we do? What do we do? So F yeah, I don't have my okay. So F of t equal to capital S t power half. Now in this equation, t is known after 15 minutes. So if you convert it to hours, it will be 1/4 of an hour. We don't know capital S. Do we know capital F? Do we know capital F? Do we? Don't we? Anybody? Prem Navneet. Do we know capital F? Okay. Nobody wants to speak. All right. So we can infer what capital F is by using the information that we have. One, we know the cross-sectional area of the tube. So it says cross-sectional area of the tube is 40 centimeters square, and 100 centimeters cube of water have infiltrated into the tube. Right. So which means, what is the depth of water that has infiltrated? If the cross-sectional area is 50 centimeters square, then capital F will be 100 centimeter cube divided by 40 centimeters square. So that's 55 centimeter. Okay. So we use this information, you put it into this equation, capital F equal to 2.5, capital S unknown, T is 15 minutes, so convert that to hours, that's 1 by 4, 1/4 of an hour. Square root of 1 by 4 will be half. So capital S will be 5 centimeter. What units will it be? Centimeter R inverse R to the power -2, something like that, right? So you will get as centimeter per hour to the minus half. Oops, sorry. Okay. So we've obtained the first half of the problem, which is to get the soil's sorptivity, which is a parameter. Okay. Now the second part of the question is, if the saturated hydraulic conductivity of the soil is 4 liters per hour, so that is capital K, determine how much infiltration would have taken place in 30 minutes if the soil had been initially placed upright with its upper surface saturated, which means the upper surface is saturated, so the water will infiltrate downwards with gravity. So then this equation is no longer useful for us. So capital F will be S times T to the power half plus K. T. K is given, S is given, T is given, solve for F, that's it. And then if you want, you can express the answer in centimeter cube of water, or you can just leave it at centimeters. It really doesn't matter. Okay. Any questions? No questions. Okay, let's move on. Let's move on. Now, what we are going to do is, just a second, we are going to use a okay. So the next method we will look at is the green amp method. Okay, now the green amp method is basically another method for estimating infiltration, similar to, I mean, just like we had the Horton's equation and the Phillips equation, now we have the green amp equation, which will also help us to figure out what the infiltration rate, instantaneous infiltration rate F is, or the cumulative infiltration rate capital F is. Now, unlike the previous two equations, the green amp method is an equation that makes some assumptions about the nature of the soil profile, the nature of moisture movement, right? It makes some simplifying assumptions and tries to say, you know what, let's forget about all this fancy 4 zones of infiltration, right? The saturation zone, the transition zone, the transmission zone, the wetting zone. All of this is too fancy, right? It looks cute, but it doesn't help us solve the problem. So then green amp says, okay, why don't we make some assumptions? Okay, make some assumptions about the soil, the soil properties, the soil, how the moisture moves in the soil, and try to get an answer. Right. So the objective is to get an answer, not necessarily only theoretically correct. Right. So that's the objective. And so okay. Anyway, so we'll discuss the philosophy of it a little bit later. But let's just try to understand how this method works. So what basically this method does is, it assumes that at time t equal to 0, before the rainfall when the rainfall is just about to start, the soil has got uniform moisture throughout its depth. Okay, so I'll just denote that with this. Initially, okay, so this line just keeps going down all the way for infinity. Okay, I've just drawn this portion. The portion that's already there on this black line is indicating the initial moisture content in the soil before the rainfall starts. That red line that I've drawn is the moisture profile in the soil at time t equal to 0. So at time t equal to 0, soil is assumed to have uniform moisture content with depth. Now, is this possible ever in the anywhere in the world? There might be very, very few situations where such a soil will be available, where this moisture content is just constant with depth. The x-axis is the moisture content, and the y-axis is the depth from the land surface downwards. Okay, so this kind of a soil will never exist, but it makes this assumption. Then, instead of having those fancy 4 zones of moisture movement, Green-Ant method says there is only one zone. There is the saturation zone. Okay, there is the saturation zone, and then there's a wetting front, and then I have the dry soil. So anything below this is dry soil. Okay, when I say dry, I mean original soil with the original moisture content. Okay, what is the initial moisture content of the original moisture content? Theta I. This value theta I is the initial moisture content. Okay, the porosity of the soil is capital N. So this arrow that you see here is capital N, sorry, not capital N, small n. That's the porosity of the soil. Theta I is the moisture content, and this N minus theta I, this gap, is called delta theta, which is the difference in moisture content until the soil becomes saturated. Okay, so that's the setup of this. Okay, so let's just go through this step by step. Now, yeah, so that's what I was trying to tell you. It is an approximate method. Nowhere in the world will you find a soil like this, but it has an exact solution. Now, there is an advantage with having a method that gives you an exact solution as compared to a method that can give you that is very precise, but will take you 10 days to get an answer that is reasonable, or that is close to being correct. Okay, or it takes, even if it takes 5 hours versus this one which does it in 2 minutes, 5 hours versus 2 minutes, this is better, even if it's not 100% correct. Okay, so that's the kind of perspective that we need to have. All right, so that's this is what I was trying to tell you earlier. It assumes that the moisture moves sharp front. So there's just one moisture profile, the saturated zone, and then wetting front. That's it. There are no 4 zones. There's only one zone, saturation zone, and then dry soil. That's it. Okay, so it assumes that this moisture is moving as a sharp front. There's a discontinuity at this depth of L. The moisture content goes from N to theta I in a sharp, kind of like a step function, right? Moisture is either N or theta I. There's nothing in between. It just goes from N to theta I, at the same, basically at the same depth. Above that, you will have moisture content equal to N. Below that, you will have moisture content equal to theta I. So that's the setup. That's the assumption. So which means, so if at any instant of time, this moisture has moved to a depth of L centimeters or meters below the land surface, then f of t, capital F of t, must be equal to L times N minus theta I, which is L times delta theta. Do you agree with that? How much infiltration has happened? It is L multiplied by delta theta at any given instant of time. At time t equal to 0, there was no infiltration. After time t, how much infiltration has happened? It is L multiplied by delta theta. Does that make sense? This is very important. Very first step. If you don't understand this, then we have trouble going on. Now remember, capital F, will capital F be greater than L or less than L? Just by looking at this, delta theta is less than 1, then it will be 0.2, 0.3, whatever it is. So if L is 1 meter, then capital F will only be 1/3 of 1 meter if the delta theta is about 30%, right? Or 25%, whatever it is, right? So the cumulative infiltration is simply L times delta theta. Okay. So I hope that's okay. Remember, we had this Darcy's law. We wrote it in terms of the Darcy velocity or the Darcy flux, small q, which is the flux per unit area, equal to minus k dou h by dou z. And remember, we spoke about we can also equate that put this in the context of both suction and infiltration. So we are going to do that now. So I will write the Darcy flux must simply be equal to my infiltration rate, instantaneous infiltration rate. So it will be K times H1 minus H2 divided by Z1 minus Z2. Now, I am taking one surface and two as the, so section 1 is over here and section 2 is over here. Okay. So that's why I've got rid of the negative sign, right? H1 minus H2 divided by Z minus Z2. Okay. So what is H1? There's a little bit of water at the surface. Above the land surface, I have some ponded water. Some water is at the land surface up to very small heights, H0. Okay. This H0 is going to get ignored in the next step. Anyway, don't worry about it. Okay. Some water has to be present at the surface to push the water down. Therefore, just imagine that there's a little bit of water instantaneously, small amount of water which is pushing the water down. So that is the head of water at section 1. H0 minus H2 is the head at section number 2. What is the head at section number 2? It is the combined head due to, remember we spoke about this in the previous class when we spoke about the total head. The total head is a combination of gravity head and suction head. So in this case, remember suction head, I said it is always negative, right? So therefore, this H2 is actually minus psi, which is a suction head at that location, minus L. Why is it minus L? If this is 0, land surface is Z equal to 0, I'm coming downwards and I'm assuming that Z is decreasing with decreasing in the, so it is minus L. Okay, so this H0 is the head at the land surface minus H2, which is minus psi minus L. Okay, divided by Z1 minus Z2. Z1 is 0, Z2 is minus L, so 0 minus minus L. So therefore, I have just simply L in the denominator. Okay. Any questions? Please stop me if you don't understand this step or the previous step, or if you have any questions about this. I could have written this also as H2 minus H1 by Z2 minus Z1 and kept the minus sign there. Doesn't matter. I just removed the minus sign because I changed the flip this thing here to H1 minus H2 by Z1 minus Z2. Okay, and also infiltration small f is positive downwards, right? By definition. Anyway, right? Okay, so no questions. I'm presuming means okay. So the next step I have just H0 is very small sigma and L so compared to psi and L. I'm sorry. So H0 disappears. H0 is small compared to psi and L. Therefore, H0 is removed from the equation. So F becomes approximately equal to K times psi plus L divided by L, right? the negative sign is all gone away. So I'm left with psi, the suction head, plus L, the distance the moisture front has moved, right, divided by L. And then I'm simply using, from this equation, I'm replacing L. So I'm taking this L, so it'll be L equal to capital F divided by delta theta. Capital F divided by delta theta. So I put that into this. So I'll get psi plus F by delta theta divided by F by delta theta. So that delta theta in the denominator disappears. So I've just rearranged and got this. Small f equal to K times psi delta theta plus capital F divided by capital F. Okay. So this is the formulation of the expression for small f. So imagine, suppose I know capital F. Suppose I know the value of capital F. I can take that number, put it into this equation. Suppose I know capital F and I know the type of soil. Once I say I know the type of soil, I'm indicating that I know what is the hydraulic conductivity of that soil. When I say I know the type of soil, I know K, I know psi, which is also a function of the soil, right? Suction head depends on the nature of the soil particles, right? And then I should also know what is the initial moisture content in the soil. If I know the initial moisture content in the soil, and if I know the nature of the soil, I know the porosity of the soil, right? So remember this. If I know the initial content theta I, and if I know the nature of the soil, then I know N. If it's sand, then N will be whatever, 0.35, 0.4. If it is clay, it will be 0.5, 0.55, something like that, right? So if I know the nature of the soil, I know K, I know psi, and then I know porosity. If I know the initial moisture content, then I know delta theta also, because it is N, which depends on the nature of the soil, minus the initial moisture content, that gives me delta theta. And if I know, all I need to know is capital F, then I can simply get small f by putting the value of capital F into this equation. Assuming everything else is known, I can get the value of small f. So now the question becomes, how do I find out capital F? How do I find out capital F? Right? It's not that we can easily measure capital L and then use that equation to figure out capital F. It's very difficult. When the water is infiltrating into the soil, you can't see where the water has gone. What is the length up to which the wetting front has moved is not visible to us. It's underground. It's invisible. So we really can't see it. So therefore, we need to come up with a method to figure out this capital F, right? So that's what we're going to do now. I will write this small f as df dt, d capital F by dt equal to K psi delta theta capital F divided by capital F. Okay. Then I'm going to rearrange this equation. I think you can probably guess what is going to happen. I'm going to take all the f terms to one side and then take the dt to the other side, whatever is left to the other side. Then you can integrate and solve for capital F, right? So that's exactly what I'm going to do. Just please watch. Because the original equation, df by dt, d capital F by dt equal to K psi delta theta plus capital F divided by capital F. I rearrange it in the following form: f divided by psi delta theta plus capital F into df equal to K dt. And then I do some some cute algebra to get it in a form that's convenient for me. And then now that I have it in this form, I'm going to integrate this equation from time t equal to 0 to time t equal to some time t, at which I want to know how much is the capital F that has happened. How much infiltration, how much cumulative infiltration has happened at time t equal to 0? At time t equal to 0, that means when rainfall has not started, capital F is also equal to 0. Then at some time t, I want to know how much capital F has happened. So I need to solve this equation. So to integrate this, I integrated from 0 to capital F of t. Oh, I forgot to put the integral on the right hand side. Forgive me for that. So it should be integral k dt 0 to t. Okay, so it will be integral 0 to t kdt. Okay. So then when I integrate this, it's expression that looks like this: f of t minus psi delta theta into natural log of 1 plus f of t by psi delta theta equal to kt. Okay, I'm not going to tell you how we got this expression. You can figure it out. So there is a 1 minus df. So you will get f minus psi delta theta log of psi delta theta plus f. Then when you apply the limits 0 to f of t, you end up with this. Okay, I'll just leave that as an exercise for you to do. Please spend a few minutes, I mean, couple of minutes, and figure out that this is indeed the form that the expression is going to take. Okay, so this is the equation that we get. Again, I rearrange this a little, get an equation f of t equal to kt plus psi delta theta into log of 1 plus f of t divided by psi delta theta. So this is the final expression for the capital F, the cumulative infiltration using the green amp method. And once I get the value for capital F from this, but it's actually not so simple, right? Suppose I know the type of soil, I know K, I know psi, and I know theta. If I know the initial moisture content, then I know delta theta. So in this equation, if I know the type, I know K, I know psi, I know theta. If I know the initial moisture content also, then I know. And then if I say how much cumulative infiltration has happened after t equal to 5 minutes, or 10 minutes, t equal to 20 minutes, whatever. So if I give you that information, then in this equation, the only unknown that is left will be capital F. But the problem is capital F is present on both sides of the equation, right? So therefore, it creates a problem. So whenever you have an unknown on both sides of the equation, what do? You can do a method. A simple way of solving this is to use a method called successive substitution, right? You take an initial guess, put it into this equation, solve it, and then check your answer. See if it is different from your initial guess. If it is different, take whatever answer you got, put it back into the equation, solve it again, and then see the answer, compare it to the guess that you put in previously. Keep doing this until the number that you put in and the number that you get out of the equation are the same, right? A good first guess would be k times t. You can assume first guess f of t equal to kt, and then put that into the right hand side, put in all the other terms, you will get another value of capital F of t. Check. It will usually be the first iteration will be different. Then again take that new value, put it back into the equation, run the equation again. Keep doing this maybe 4 or 5 times, and then your equation will converge. Solve it by successive substitution. The first iteration you can use k of kt, f of t equal to kt as your first guess, right? So once you get f of t, capital F of t, you can simply take that value of capital F of t, put it into the other equation, and you will get F, right? So that's the method that you can adopt to solve for the infiltration rate as well as the cumulative infiltration using the green amp method, right? So we will go over this once again on Friday during Friday's class. We'll just spend a few minutes on this to quickly get this over with. If you have any questions, please send me email. Anyway, we'll meet on Friday, so then we can have a discussion on this. Okay, take care. See you all on Friday. Looking forward to it. All right. See you all. Bye bye.